Okay, sounds good. All right. So hi, everybody. I'm Emery Berger from the University of Massachusetts Amherst. I'm here in my role today at large the SIG Plan Executive Committee, specifically in my role as one of two EC members in charge of a variety of awards granted by SIG Plan. I'm delighted to be able to present the second of two awards this week. Yesterday, it was the POPL Most Influential Paper Award. And today, I'm delighted to present the Robin Milner Young Researcher Award. So let me, before I announce the winner, let me give a little bit of background about this award. The Robin Milner Young Researcher Award is given by SIG Plan to recognize outstanding contributions by young investigators in the area of programming languages. It's a 20-year award, so young has a creative definition. The eligibility can be adjusted as well for special circumstances, such as, but not limited to, family leave, medical leave, or military service. The award includes a prize of $2,500. And the committee includes the chair, who's me, as well as members of the major SIG Plan conferences, POPL, PLDI, ICFP, and SPLASH, who are respectively appointed by their steering committees. So before I announce the winner, I just want to thank all the committee members for their hard work this year. The committee members were Michelle Strout of the University of Arizona, who's the PLDI representative, Derek Dreyer from MPI, who's the POPL representative, Ejiro Sumi from Tohoku University, who's the ICFP representative, and Todd Milstein of UCLA, who's the UPSLA SPLASH representative. So on behalf of the committee, it is my great pleasure to present this year's Robin Milner Award to Eran Yahav of the Technion. So can all applaud. Let me read the citation for Eran from the committee. For those of you who are not familiar, Eran Yahav has a record of sustained high impact contributions to the programming languages research community over nearly 2 decades. Much of his work has been about effective static reasoning about concurrent programs, which is a longstanding challenge due to the complex and non-local ways in which threads can interact with one another. Yahav developed novel abstractions for verifying safety and correctness properties of concurrent programs and used them to validate non-trivial concurrent algorithms in Java. Later, he extended and applied program synthesis techniques to concurrent programs in creative ways. For example, demonstrating how to synthesize a correct concurrent version of a sequential algorithm and how to automatically repair an existing concurrent algorithm through additional synchronization. Most recently, Yahav has been an early leader in the area of big code, leveraging machine learning techniques to solve difficult programming tasks, including code search, code completion, and reverse engineering. This work has influenced others in the research community to pursue this research direction and has led to practical software engineering tools for programmers. So again, I'm pleased to present Eran. Eran is going to be presenting a talk that's roughly 50 minutes long about his work and reflections on what he did. So take it away, Eran.
All right, thank you very much, Emery. It's a great honor and pleasure to be here. And I think this talk would be nice if we can ask questions during the talk, and I've shared an AMA link in the Zoom chat because it's hard for me to keep track of the Zoom chat. So feel free to ask there, also anonymous questions and comments. And let me just share my screen here. All right, so all right, again, it's really a great honor and a pleasure to be here. And I'd like to spend our time together talking about neural methods for programming language processing, what we call, and in particular, structural language models of code. And let me just fix this. All right. All right, yeah. All right, and while I'm the one giving the talk, this is really the work of many great talented students over the year. There are a bunch of papers, relevant papers that you can look at later listed here. Most of what we do is available as open source, and there are GitHub links here on the slide, and some has been commercialized by Codota. And today I'll talk about mostly work by Uri Alon, Shaked Brody, And if we had time at the end, we'll touch a little bit on what Gail is up to. All right, so just to set the scene, I spent many years, as Emery said, using this kind of setting, doing abstract interpretation, taking a program, putting it into some abstract interpretation machinery and trying to show that a property, some property phi holds for this program. And in order to do that, usually the abstract interpreter designer, me, had to provide some PL syntax into the mix and usually some abstract semantics as well. And you can do a lot of cool stuff with this, and we did, but the context of this talk is very, very different. In this talk, we're going to replace this reasoning machine, the symbolic reasoning machine of abstract interpretation or type systems, if you prefer, with a machine learning neural model. And to make this model work, we're not going to give it any abstract semantics or programming language syntax or nothing, actually. We're just going to train it by using a huge number of examples of pairs of programs and the property that we would like to infer. And once the model has been trained, we're going to present it with some unseen program, like the program P here, as test data, and see what the model says. And as we do that, we will have to give up the notion of absolute correctness. We will not know that the property phi holds for this program, but we may know some probabilistic guarantees from the model such that, some property A holds with probability 77.34%, and some other property B holds with another probability, etc. So that's the setting of this talk. And to make it more concrete, let me give you a few examples. So here's a simple example and code written in Java. And the task here is to predict that the property that we would like to infer is what is the name of this method, what is a likely name for this particular method. And this is work from POPL a couple of years back. So I'll give you 10 seconds to look at it. We're trying to predict what is shown highlighted in yellow here. And I think maybe any suggestions? I heard reverse. So yeah, this is reverse array. And you can get that by putting it into code2vec, and you can try it right now because you're all next to computers. So you can go to code2vec.org and play with the site, see the examples. And this is what the model gives for this particular piece of code. And the interesting thing, if you look at the code itself, you will see that the word reverse does not appear there anywhere. And actually, it's quite hard, if you have not seen these things before, to generalize from the combination of low-level operations here that what this program is doing is reverse. So let's look at another example. Here's another example, this time code written in C#, and the task is different. The task is to predict a caption that describes what this program does. And again, I'll give you like 2 seconds now because I don't want to spend too much time, and I'll show the result. And the result is, again, predicted by a model we call code2seq, also a couple of years back. And the caption that this model predicts for this program is replace a string in a text file with some probability. And there are other alternatives. I'm not showing them here for simplicity. In this case, we generate the entire natural language sentence. So replace a string in a text file from this code, which is kind of cool. And last example I want to show you is very different. In this example, we're not going to generate any natural language description. We're going to actually compute some code completion for this piece of code. So again, there is some code given here. What we're trying to predict is highlighted in yellow. And using our latest structural language model, what we can predict here is the completion stats I get path with some probability of around 12%, which is the correct result for this example. And for the rest of this talk, mostly I'll focus on this kind of thing, on code completion, and I'll show you the mechanics of how this stuff works and what we need to make it to work. All right. And so I'd like to just dive in right into the details here. And so let's dive into the details of how this neural model works. And the first question that we have to answer is how to represent code in neural networks in general. So on the left-hand side here, we have a program saying hello world. On the right-hand side, we have some neural model, in this case, a transformer encoder. And the question is this, on the left, the the program is a discrete object. On the right, there is a neural network working on continuous numbers, and we need to bridge this gap somehow. We need to feed the program into the neural network in order for this to work. And there are many ways in which we can do that. One of them is, one simple way is to use sequence-based model. And the idea in sequence-based model is to represent the program simply as a sequence of tokens or sequence of characters or sequence of byte per encoding, BPEs, and just feed that into a standard sequence model for the garden variety of sequence models that exist in NLP. And the good news is that it's very simple. It's almost trivial. There are many sequence-based models that you can use, which are directly applicable, LSTM, simple ones, transformers, whatnot. The downside is, of course, that the model is not aware that what it is being fed is a program. It knows nothing about the sequence of characters, and it has to basically waste capacity by implicitly relearning the known syntax of the programming language. That makes it very data hungry and also requires large model because the model needs to basically generalize over the noisy signal of the different sequences in order to relearn what it means to be a valid program. And as sequence models go, you probably know some of this at least. Recent years have seen an explosion of pre-trained language models. So in 2018, 2019, we had models with millions, tens of millions, hundreds of millions of parameters. And somewhere in 2019, we had the GPT-2 with 1.5 billion parameters. And then came 2020, and we have GPT-3 with 175 billion parameters. So this keeps growing, and these models are extremely powerful. They are basically universal predictors of sorts. They can predict very effectively anything that can be encoded as a sequence, and programs are not an exception to this rule, right? But this keeps on growing, and it's kind of interesting to see if this year we will hit the trillion model, a trillion parameter model. So that's kind of cool. And I'd like to now show you what these models are capable of doing, because I think that this is at least nice to see. I'll try a live demo, although I don't know what will happen because the model is sampling. So let's try to ask the model, this is GPT-3. Let's try to ask it what is POPL. I hope that you can see my screen. And this is a really disappointing kind of answer. So because the model is sampling, I'm brave enough to try again. All right, so POPL is the yearly conference on programming languages held in the US. Okay, that's already kind of wrong, but okay, let's try again. Conference sponsored by blah, 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 blah. Okay, this seems like, but it looks like it memorized a lot of source material in order to do this. So this is kind of maybe not super interesting. Let's look at something else then. Let's look at translation. So I have a Java program here, like hello POPL, and I want to ask GPT-3 to translate it to Python. So everything that you see here in bold is the prompt, is the input sequence to GPT-3. And I ask it to translate it to Python. And basically, if you can read this is, the program is very simple, to be honest, right? But this is not bad, right? This is pretty good. And we can try another one and see what it says. Right? It even says the Python version is much shorter than the Java version. It tells you like it complements itself, kind of like it's nice. Let's try another one, last one, just for fun. So I asked GPT-3 to write a Python program that multiplies two input numbers A and B, and then subtracts an input number C. And can try and see what happened. Okay, that's kind of like let's do that. Hang on. Okay, this is very disappointing. I had much better results earlier when I tried this. I'm trying again. Okay, this looks a little better. It's hard to read, but you can see that it got the gist of it. So it's A, It even does the casting to int, input, enter number, and the result is, this is the important part, A times B minus C. So it kind of figured out, I think it's kind of, it's impressive. And I think the question in all of your minds is like, is this you know, a party trick or something that can actually work in practice? And so I knew that this will not work for real when I tried. So I had like pre-recorded versions here on the slide for GPT-3. And you know, the question of whether this is a party trick or something that can work for real is interesting. And I encourage you to check out Dijkstra note EWD667, but I will not get into it during this talk. You can all Google. And for the question on whether this could be made to work for real, or is this a party trick, then you know, it can be made to work for real. Like in this case, this is tab 9 based on GPT-2, but it takes much more work than just using the naked model. So again, the generation here, I forgot that I should say this, that there is no specification. We're basically doing code completion without knowing what we're completing, other than hints provided from the context in which we compute the completion, right? So that's the setting. This is not sketching or anything that has a formal specification. We're just trying to complete the most likely completion based on context. And again, I'm brave enough to maybe, or stupid enough to maybe try to do it live. Let's see if this works. So again, I can go and I say something. I have an array of items here. I can go like take first item from the array. Like string first. This is okay. That's nice. Then you know, it also completes the comments that okay, you probably want to take either the second item from the array or the last item from the array. I kind of know what you're trying to do. Let me take the last because this is like more impressive maybe. Again, you just get this, all right? So again, it can be made to work, but it's a lot more than just the naked model. And so basically these are still like huge models at the end. There are like, as I said, billions of parameters or 175 billion parameters for GPT-3, and billions of parameters to train means millions of dollars. And this is becoming very big. And even worse than that, it's getting very hard to improve this by just increasing the model size. And so you're hitting kind of like diminishing returns on increasing the model size, and the dollars keep on going. And so as a result, there's a lot of work in the machine learning community on reducing model sizes by pruning, distillation, and whatnot. But in our little neck of the woods, you know, when we work on programs, maybe it's better for us to try and leverage the structure in programming language syntax and semantics in order to hopefully get models that are orders of magnitude fewer parameters, but obtain the same results. So more generally speaking, this is kind of a hand-wavy trade-off graph of the learning effort on the vertical axis versus the program analysis or semantic depth on the horizontal axis. And what we just used is we used learning on the surface text of the program all the way to the left. And what this does, it implicitly has to relearn the programming language syntax, right? Because it knows nothing. It's just a sequence of characters. And this hits some feasibility barrier, either in terms of training time, training data, the dollar spent, or whatever. You cannot do this forever. And this motivates us to go further to the right in this graph. And this is really nice work that does that by Alamanis and Brookschmidt from Microsoft Research, that a few years back started representing programs using graph neural networks, GNNs. And the idea here is very appealing. You take the program and you create a graph very similar to data flow graphs that we're familiar with. You take nodes to be occurrences of variables, and you take edges to be some flow of semantic information like data flow or control flow. In their case, for example, these blue edges are the last write to the variable occurrence. So you can see how the information flows between occurrences of X and Y. We can have other edges showing the last use between variable and edges showing where each value is computed from, etc., etc. And this is really compelling. I think for us as programming languages people, this is a natural match for programs. We've been doing this kind of graphs forever. It's easy to design and include more features by adding new kinds of edges. But on the downside, the semantic analysis is really expensive and restrictive. We are trying to train on large amounts of code, and what this requires, it requires that we compile each piece of code. Most of them, cannot be really compiled. Definitely, if you grab random stuff from GitHub, it's going to be very hard for you to build it, and very hard for you to get to the point in which you can extract this kind of semantic graphs. Further, all this feature design around what edges you need, etc., is very language and task specific. So if you're trying to do code completion for Python, it's going to be one thing. If you're trying to do type prediction for JavaScript, it's going to be something completely different. And we'd like something that is much more general. And so we saw that if we go all the way to the left, we get hit by this feasibility barrier. If you go all the way to the right, you become very language specific and task specific, which requires expertise and requires like a lot of effort per task. And so this motivated us in my group to look at somewhere in the middle, trying to find the sweet spot on this trade-off, something that gives you model compactness, but also language and task generality. And in a sense, this is what we found out is that things that work really well are things around ASTs, abstract syntax trees. So things that leverage the language syntax, but not really the language semantics. And the idea is to try and basically do as little program analysis as necessary, or a little analysis as necessary to really cut the majority of the learning effort in order to make this scalable and generally useful. And so one of the main ideas that we introduced in 2018 was abstractions that are using AST paths. And the idea is the following. On the left here, you can see a simple while loop. And we're going to represent interesting facts about this program using paths in the abstract syntax tree of the program. So on the right-hand side here is the abstract syntax tree. And a path in the syntax tree is just a path, in this case, between two leaves. So I'm going to pick the two instances of the variable done, also in the tree. And I'm going to show you a path, which is starting from done, going up to the symbol ref, to the unary prefix, to the while, then going down to the if, to the assignment, to the symbol ref, and the same done. And what you see at the bottom of the slide is the path between these two done nodes. And it seems quite silly. So if you think about it semantically, it's like, what does it even mean, this path between two instances of done? It's nonsense. But if you think about it a little deeper, you see that this path captures the notion of doneness as a feature. If you look at it as a feature of the variable, you see that this is a variable that is used under negation inside the condition of a loop and is assigned inside the loop under a condition. So if I ask you to describe, hey, what is a stop condition for a loop, you'll say it is something that is used as inside the loop condition, usually with negation, and then assigned somewhere inside the loop under a condition. So this kind of shows intuitively, at least, why these paths manage to capture interesting properties about programs or about parts of programs. And when we come to represent the program, we don't represent it using a single path, we represent it using all paths in the AST. And so if you look at these two programs at the top here, two procedures, both of them are counting occurrences, but they do it in very different ways. One of them is doing it using do while, and the other one is using a for loop. The one on the left is doing index of, the one on the right is doing car at. So they are very different. They do the same thing. If I ask you if they're doing the same thing, you'll probably say yes. If you look at the ASTs and paths in the AST, you will see a lot of resemblance in parts of the structure. So despite the fact that the programs are very different, you can see that the red path, the blue path, and the green path here are quite similar, and this allows the model to do it. It allows models to kind of generalize over syntactic differences that you would see in the program text and still capture some of the structural features available in the AST. So again, the intuition is that because we're inserting the structure of the program into the model, we are enabling it to generalize a little better. All right. And indeed, we use this quite successfully in our code2vec work. And I'm not going to go deeper into that. You can try the website yourself. But in this talk, I'm interested not in predicting like program labels or program captions. I'm interested in language modeling of code. And language modeling is the problem of assigning a probability to a piece of code, right? So you give me a piece of code, I tell you how likely this piece of code is to appear in the universe. And if you can answer this question of given a piece of code, assign it with a probability, you can do code completion because you can say what is the most likely completion given some partial code. And you can also do code validation because you can flag code as being unlikely. Say, oh no, Eran, this red part here is unlikely. Why? I don't know. Like I can tell you as a run that array does not have size, it has length, but the model just knows that this is very unlikely piece of code. So how are you going to do that? So there are the idea of language modeling is obviously very popular in natural language. And in natural languages, you look at it as assigning a probability to a sentence, right? So you can use it to predict a missing sentence in a sequence of text or a missing word in a sentence. But the way we would like to look at it is instead of looking at code completion as a sequence completion problem, we'd like to look at the code completion as a problem of predicting a missing subtree in a tree. So you give me an AST, a partial AST. I would like to complete the missing part of the AST. And what this allows the model to do, it allows the model to learn syntactic patterns instead of look at sequential patterns. Right? So again, it's the same idea, use the structure of the program. And this idea at the high level, the high level idea is not new. It has been used in the neural setting by Madison and Tarlow in 2014. And if you look at NLP setting before neural, the idea of predicting subtrees is probably 98, 96, something like that before neural times. But the details, of course, differ. So in natural language, when you look at the probability of a sentence, it is usually computed by decomposing the probability of the sentence to the product of the conditional probability of a word in the sentence conditioned on the preceding words in the sentence and the words before it, right? And now we're in a jam, right? Because what does that even mean for a tree? Right? We need to define some sort of a similar notion in order to compute the probability of our trees. And the first thing that we do, we induce order over the nodes. So you look at the nodes of the tree and you induce some order. In our case, we found out that I think left to right DFS worked best, but this is just a practical thing. You can induce any order that you want for the generation, And the way we define the probability of a tree is just the product of the conditional probabilities of taking some node given a partial tree. So predicting node, basically the way you can look at it is I'm trying to predict a node. I'm trying to build the tree node by node, where the conditional probability is for a node given the partial tree of all nodes that preceded in the order. Does that make sense? So basically, it should be very natural to people who have done top-down synthesis. We're just building the tree node by node. Every time we take the conditional probability of the step of adding a node based on the partial tree that we've built so far. So that's the high-level idea, but we're still stuck because it is not clear how should we represent this partial tree when computing the conditional probability of the node giving all preceding nodes. And this is the third piece here of the puzzle, which is the important one, where AST paths make a re-entry here. And basically, we compute the probability of a node in the conditional probability of a node conditioned on the partial tree by considering all the paths in the AST from leaves to the node. So again, for people who have done top-down synthesis, this is again natural, because what we're doing is we're looking at the node and we're looking at the context of all nodes that already exist in tree and try to propagate this information back to the node in order to make the decision. So let's zoom in on this process. If this is the entire AST and the blue piece is the kind of missing chunk of the tree that we're trying to predict, and this pink thing is the node that we're trying to predict. In order to predict this node, what we're going to do, okay, just a second. Okay, I don't know, Adam is asking a question, but I'll get to that in a second, Adam, sorry. So the pink node is what I'm trying to predict here. And in order to do that, I'm taking the path from the left part of the tree reaching the node and the paths from the right part of the tree reaching the node. And I'm also adding another path to the mix, which is the orange path here from the root to the node, which gives me the state of the prediction, kind of like how far, what is the location of the node that I'm trying to predict other than the context in which it appears. So I'm basically using three pieces of information, paths from the left, paths from the right, and kind of an index from the tree that tells me what is the step in the generation process. And the beautiful thing about this approach is that it can be instantiated using different encoders for different steps. So for the first step, what I need is I need any sequential encoder to take a path of arbitrary length and compress it, represent it as a fixed size vector. So that's the first step. Second step is I need to kind of mix, contextualize all the paths that reach the node, basically let them interact with each other and get relative weights of which paths are more important than others. And at the end, I need to attend or basically query all these paths that reach the node with the path from the root in order to make the decision of which node to predict. So again, at the high level, I think it's not really important that we talk about specific ways to do it. Encoding paths, you can do it with LSTMs or with transform encoder. Then the contextualization, basically you can do again with transform encoder. You're trying to mix the path, get relational information between them. Then you attend to it with a query, and that gives you the prediction of the node that you would like to predict. And again, let's look at a concrete example. Maybe it will be easier to follow. Let's have this missing piece in blue, and I'm trying to generate the tree of x greater than 1. So I start by generating greater. That's the first node, just showed you. Then I go to the left. I take the context of all the paths from the left, all the paths from the right, and the orange path from the root. I generate the name. And at this point, I generate x. And at this point, something interesting happened, which is taking also the context from the things that I have generated so far. So that's kind of an important step in this generation process, in which we're also contextualizing on the partial things that we have constructed thus far. Okay? And I keep on doing this process, and I get x greater than 1. And once I have this piece, I can, of course, transform it back to code and show it as a code completion to the user. And so that's at the high level of the process. The neat thing about AST paths is that they allow us to capture long-range interaction. One thing that I did not tell you about the sequence models when I showed them is that their context going backward is quite limited, right? Even in the most advanced models, this is like whatever, 1024 tokens, BPE tokens, or something like that. And in programs, often the locality is more problematic. You have fields or something that are defined high up, parameters of a function that are maybe further than the context available to the sequence models. And the neat thing about AST paths and this structural language model is that it allows us to capture these long-range interactions. So if I look at this example, trying to predict what is shown in green here, I can predict this stats I get path. And when I predict stats, I'm basically attending to the information from the parameter of this function, showing that the variable stats is of type array. And when I'm predicting I, this is quite local, but I'm attending to the part that, or I'm using the information that this is an integer. and can be used as an array index. And to make the decision that this node get path, I'm using maybe the fact that ret, what I'm assigning to here, the result, is of type array of paths, and I'm addressing a single index of it. So again, I don't want you to follow all the details. The high level thing is that using the structural language model, I'm able to get information flowing from long range in the program, which is very hard to do with sequence models. So some more examples. Here's a Java example. Again, I think we've seen that example in C#. You see this is quite expressive. It gives me the substring with the right numbers. And again, it knows, I think the shocking part is that it knows nothing about the semantic of the program, right? The only thing that it knows is the syntax, and it still makes very good predictions. And you can try, don't take my word for it, you can try it yourself. It's anycodegen.org. There are many examples available there. You can put anything like with 2 question marks and get predictions, and it will also show you on the right-hand side the AST that it constructed to make this prediction. In fact, what I showed you so far is something that works only for expressions, but there's an extended model available on the website that you can also use to predict complete statements. So for example, if you look at this program, going back to concurrency times, and you see that it does unlock at the end, in this program, we can predict that the completion here should be locked, taking the lock when you enter the methods, when you enter the method. And again, it knows nothing about semantics, right? This is purely syntactic stuff, but trained over tons and tons of examples. And so what I showed you so far is kind of 3 ways to do code presentation: the textual one that is structural based on AST path, and the one by Alamanis and Brookschmidt that I mentioned earlier with graph neural networks. And it's interesting to look how they perform in reality, right? And so this is the comparison of accuracy at 1 and accuracy at 5. Accuracy at 1 means that what is the accuracy at the first suggestion, the first completion. Accuracy at 5 means we look at the top 5, and if one of them hits, we count it as a hit. And not surprisingly, when you see this kind of graphs, our work is the best, right? So nobody's shocked. But what is, I guess, shocking, or at least was shocking to us, is how poorly the GNNs do here. Because based on my hand-waving explanation, at least, you would have expected the graph neural networks with the semantic information to do much better here, right? And so it's quite surprising that they do so poorly and worse than the sequence models. And that piqued our curiosity. So Uri, the great student who is doing this, was like, this makes no sense. We must understand what is going on here. And we started looking into GNNs. And I think for the program analysis guys who probably did not like very much the syntactic success, this is more kind of semantic. This is very close to abstract interpretation stuff, graph neural networks as message passing networks. So the idea in graph neural networks that you start with a graph where each node has some initial representation of embedding of features, so it has some value basically. And at each step of the network, we propagate information between the nodes, and the node aggregates the information that arrives from its neighbors and aggregates it with its own information as well. So on step 0, each one has some value, age of the node. You make one step, it takes information from all the neighbors and aggregates it, make another step, take all information from the neighbors and aggregates it. So if you, I think I can do this, can I? Hang on, let me try. So basically, if you want to think about it in program analysis terms, like the value at step of this guy is basically the value at step 1 of this guy, value of step 1 this guy and the value of itself. In step one, and you take some join, basically, if you want to think about it in program analysis terms, right? So you just take this information, you aggregate it into the node somehow. All right, and so the interesting thing here is that we know that the GNNs are very good for short-range tasks. This is not from the literature, so there's a ton of work on using it for things like paper subject classification. You look at the papers, and based on other papers in the neighborhood, you classify into subject or friendship and collaborations in a social network, looking at kind of the friendship relationship and determining whether other friends should be added, etc., etc. But these are very local properties. They require 2 or 3 message passing steps. But our tasks in talking about programs, as we just saw earlier with the ASTs, we need some long-range relationships in order to draw conclusions. And so we try to understand how do these things really work, how GNNs really fare when you throw long-range problems with long-range dependencies on them. And we designed this contrived problem of neighbors match. And the idea is the following: in neighbors match, I give you a query. And the idea is that you have to find the node in the graph that has the same number of neighbors. So in this example, the node with the same number of neighbors is C. So you have, the blue neighbors. So you need to find the node with the same number of blue neighbors. In this case, it is C. And it turns out that if you look at this problem with large graphs, deep graphs, where you need the number of steps to be, you need number of steps to be larger than how far C is from the query. In this case, it has to be at least 4. What happens is the following: if you look at the propagation of C alone, then you make 4 steps, and you found out that C is the node that has 2 blue neighbors, and you're happy. But as the GNN work, as GNNs work, it's not that they propagate only the information from the target node, which is obviously unknown. They propagate information from the entire graph. And what this means is that the receptive field of the node, like the information that flows into a node, is growing exponentially with the number of layers. Okay, so as you go to longer and longer distances, because the way the GNN works is that it aggregates information from all the neighbors all the way up, you're getting the problem of over squashing. You need to basically, if you need to flow a message for a distance of 4, you need to squash it to 0 degree of the power 4. And so basically you get some bottleneck where you have to take an exponential amount of information and squash it into a single vector. Right, and so into a fixed size vector. And this, of course, doesn't work very well. In a sense, it is similar to the bottleneck that, in recurrent sequential models before attention, that you only had a single vector capturing everything that comes out of the encoder. But then in RNNs, it was a linear bottleneck. It was dependent linearly on the size, on the number of steps, and here it grows exponentially with the depth of the network. So this is really bad news, and it's such bad news that even at depth 4, some GNNs cannot reach 100% of training accuracy, not even in tests. So they cannot fit the training data at depth 4, which is really, really bad for programs, because programs typically, from our experiments, or from Brook-Schmidt's experiments, need at least depth 8. Okay, so I'm going to skip a few things here. And worse than that, again, because it explodes exponentially, then you may think, okay, let me just make the dimensions of my network larger, just expand the length of vector and it will be fine. But if you want to do a 2x increase in the message range, it costs you 8x increase in the dimensions. So this is not going to scale. You need something else. And so we looked at real life models. Again, I remind you that the motivation for all of this was basically that we saw that GNN does very poorly when we compared to it experimentally to our models. And then we said, okay, there's a bottleneck here. We observed, how do we solve it? Let's do the simplest thing possible. What is the simplest thing possible? Let's destroy the structure of the network on the last layer, just connect everything to everything in the graph. So everything becomes distance one hop. You don't need to propagate anything for long range. And this immediately got us like 1% accuracy increase in var misuse. This is a trivial solution. It's not even a solution. It's just showing that the problem exists. It's not even a solution. But in other problems like predicting properties of molecules, we reduced error rate by 40%. We got 5% error reduction in some biology problems, and 12% error reduction in classifying enzymes. So it's kind of like, it's crazy because this doesn't show that our solution is good. It shows that the problem is very prevalent, and even a trivial solution gives you some gains. So basically, we just show the problem, and better solutions are waiting to be invented here. And I actually think that the program analysis kind of background is perfect for improving what is going on in graph neural networks. So this is for all of you guys to look at. So the last thing I want to mention, because I did manage to reach here within the time, is the work done by Gail Weiss. This is quite different from what I talked about so far. So we had a bunch of results on computational models for recurrent neural networks. We showed together, or it's actually Will Merrill's work, a formal hierarchy of RNN architectures. How do they relate? How do they differ in their ability to identify formal languages? So the idea here of this kind of line of work is to use formal languages as a knife to dissect different neural architectures, separating different architectures based on their ability to identify formal languages. And while doing that, we also had some work on extracting automata from a recurrent neural network, et cetera, et cetera. Look at that later. And then we got into this question of how do we do the same thing for transformers? So transformers are much more elaborate than RNNs. Question is, what is a good computational model for transformers? And this is what Gail has done with the restricted access sequence processing RASP. It's a programming language that has the same access pattern as transformers. And you can basically write programs that run on the transformer hardware. Basically, they compile down to transformers, and they can only do what transformer can do. And this is just an example of reverse. So on the left-hand side, I will not talk about the details of the language in 1 minute, obviously. On the left-hand side here, there's a RASP program that does reverse using transformer abstractions. And on the right-hand side is what the transformer has actually learned. And the beautiful thing is that we can write programs as humans that are later reflecting, or they capture the tricks that transformer does when it learns to perform the same tasks. So again, this is very, very high level, I know, but we will not have time to go into it. Talk to me about this offline. What the language allows us to do, interestingly, is to predict for a certain task what would be the number of required layers and required attention heads to solve it. So, or to solve it in our way. So at least for one solution that we devise, what would be the requirements of number of layers and number of heads. So that's basically what I wanted to talk about. I showed you a structural language model of code that is very general. It's a language model over trees. It's predicting, doing the prediction by predicting the missing subtree, and really strong with long range information propagation. And I showed you this bottleneck in the GNNs, which is really a prevalent problems in GNN that is waiting for a real solution and not our kind of strawman solution that we provided in the paper. And that's all I have, guys. Thank you very much.
All right, thanks, Eran. That was great. Let's everybody unmute and applaud, or you can use the emoji. So there are a couple questions that had come in on the Zoom. If you all have any other questions, we have a little time to take some. One thing I did want to mention, just so everybody knows, so I don't forget, I posted this on Zoom as well, but there's going to be in an hour papers that, as you know, there were some technical difficulties. So just wanted to let you know about those, and please take the time to go visit in an hour or so. So let's see. So I think that Adam had the first question, and then Rupsha had a question. Do you want to just go ahead and read those, Eran, or should I read them?
If I can find them.
All right, I'll go ahead and read it. So Adam says, the example you just showed, this was half an hour in, looked like it could have been replaced by a one-liner using array map, the higher order function. Have you studied how to use ML techniques to give refactoring advice, like replace with call to the following library higher order function?
Yeah, so I think that's a great question. We have work in UPSLA, which is not exactly what you're asking, Adam, but it is talking about edit completions. So just like you do code completion and predict the missing part of the program, you can do edit completion and predict edits based on past edits. So this pertains to refactoring and to other things, which is, it's a very natural, I think, question. Yeah. Problem there is to get training information. For many of these tasks, the problem is to get high quality training information. So for refactoring, if you're not careful, what you'll end up learning is what standard IDEs have as refactoring transformations, because most of your training data would be based, or the clean repetitive training data would be based on these.
So just a technical question on that to follow up. Where do you get training data for this sort of thing? I mean, are you pulling this from like Codota instrumentation, or is that where the training data is coming from, or somewhere else?
For edit completions?
Yeah.
For edit completions from commits on GitHub with a lot, with ton of pre-processing. You need to like suffer to clean this. Yeah. And
yeah, I was wondering if GitHub was the source, but I immediately ruled it out because I figured that would be impossible. But all right, I guess it's possible.
It's possible if you have someone as determined as Shaked Body to like bang his head against this. Yeah.
Awesome. Okay, so Rupsha asked, have you considered representations based on semantic features of programs that also manage to hit some sweet spot in the learnability versus human expertise curve you showed earlier?
So I think the GNNs are pretty much of a sweet spot there. And I kind of left it hanging in the talk of why GNNs did so poorly at the example that I showed, because the bottleneck was not an explanation, it just improved it in 1%. So the reason that the results were so poor was actually the data set has problems, and it's kind of it's overfitted to the data set in a sense, and you can do better with GNNs. They don't have to perform as poorly. So if you look for semantic features, I would definitely recommend to represent them using GNNs. It's expensive, so if you're trying to build a practical tool, that's not where I would go as a first step. But if for research, that's definitely what I would do. It's also getting better all the time.
Okay, great. So Fritz Henglein has a question. He notes that trees are a very friendly class of graphs, tree with one. Can that be exploited? And he even comes up with an acronym, TNNs.
So there are three what's called three RNNs, three neural networks. So basically fold and unfold. So you can do all sorts of things on three RNNs. It exists as an architecture. It is quite powerful. So yes, it is a friendly kind of graph to work with. And people have done that, including us. But you get, actually, we did not mention it in the bottleneck paper, but you get into a similar problem because when you're doing three RNNs, all the information is basically propagated to the root, and the root becomes a bottleneck again. So you get the same kind of bottleneck exponential explosion in three RNNs as well. Now that I think about it, we didn't even say that. So yeah.
Great. So other people should obviously feel free to continue asking questions. Fritz notes, in routing, fat trees are used to avoid bottlenecks.
Oh, I didn't know that. That's interesting.
So I have a question. So your examples seem to be Java, C#, which is basically Java. What happens with other languages that are not all Java? Are there languages that pose particular challenges? I mean, I could imagine that higher order languages would be more complex to deal with. They wouldn't maybe carry as much information. It wouldn't be as local. You know, Haskell programs tend to be kind of very small bits spread everywhere. So if you could speak to that, that would be great.
Yeah, so I think, yeah, it is easy for languages such as, you know, C#, Java, same thing, in which there's a lot of boilerplate and therefore like a lot of kind of hints from the context on what should be there. You get very high precision just from the boilerplate. It is equally easy in JavaScript, surprisingly. It has enough repetitive structure. Haskell and company, I don't think we have like experimental results on these, but I imagine that they are much harder. You can get into trouble with 5 characters, right? Like the difference between a correct program and an incorrect one, it could be very small footprint in terms of the number of characters. And so I'd imagine it would be much harder for that kind of languages. Yeah, again, these models are, you know, it's not magic. It draws on repetitive stuff. And if all the programs are one-off functional sophistication, then it's going to be much harder to predict things. Okay,
so we have 2 more questions. I think we have just enough time for both of these. So I'll give Philip a chance to go first. So Phil asks, this is Phil Wadler, can you give a simple example to explain why your path-based technique doesn't hit a bottleneck? Doesn't the number of paths through a tree grow exponentially with the depth?
Yeah, that's an excellent question, and the answer is that the way in which the paths are aggregated is what is the simple explanation? Simple explanation is that when you're making the decision on how to combine the path, you have the full information for the path itself, whereas in the GNN you're doing the joins as you go up the tree. And so basically you can think of it as in program analysis terms as composing the transformers, this time abstract transformers, before making the decision. So it's kind of the join over all paths instead of doing join on every step. Does that make sense at all? So there's still exponential blow up in the number of paths, but you're not losing information too early in the process of joining them, right? So definitely there's an explosion there as well. No magic.
Great. Okay, so let's end with this question, which is a great and hilarious question. So Adam Chavala says, if the bad guys realize everyone is using tools like the ones you were showing off, what are the crafty ways for them to poison GitHub and get everyone's code completed to send them lots of Bitcoin?
That's a fantastic question. And so the answer is that we're not doing much more than automate something that is already happening, right? So people are already, most of the code in the world is probably copy pasted from Stack Overflow. And so the question of poisoning Stack Overflow is already an open question. I'm sure it has been done before. Yeah, but it is an interesting question. I think there is an even more dangerous question, which is if you've seen works on adversarial examples for neural models, the question is, can I change the context in a very subtle way, the context in your IDE such that the predictions would be something that I would like to get. So I can actually guide your completions without you even noticing. And we've had some work on that in recent UPSLA, which is kind of nice. Yeah, but you know, as you're accelerating things, in this case, accelerating code prediction and code generation, you're also accelerating the bad guys inevitably. And so I don't have an answer. When you don't have formal specifications, all bets are off anyway, right?
There was actually a paper, I don't remember if who the authors were, but it was about finding errors in the way people use cryptographic protocols. And there's lots of inadvertent poisoning of Stack Overflow where there's bad advice that's been given that would lead to people misusing the protocols. So this is already happening, probably by accident, incompetence rather than malice. But anyway,
yeah.
Eran, let's give a round of applause to Eran once again.
Thanks, everyone.
Now I will pass the mic to Andreas.